Hello there, welcome back. And on our screen today, we are going to run a very different, special, for the first time analysis, which is a temperature sweep or temperature analysis. It means all the circuits that we designed in an industry or in a research are basically designed to operate at a room temperature that is at 25 degrees centigrade. Okay, 25 or 26. Now, when you design a circuit, discrete or integrated, you basically tend to expose your circuit to operate at higher temperature or lower temperature, not necessarily always at the room temperature. So usually you see when you buy any integrated circuit and temperature range is specified, for example, minus 40 degree to plus 150 degrees centigrade. So the manufacturer says that, okay, between this temperature range, your circuit or the integrated circuit is going to be performing within an acceptable limit. So you can tolerate the performance. So we have seen the reference circuits, current references, voltage references, and we've seen the current mirror circuits also. And there, using the current mirror, we saw that we are able to produce an output current when we are operating in case of a BJT. We said that, okay, the transistors are biased in the linear region. So we have an operating point, and this is the collector current. This is the output voltage between collector and emitter. And we said that transistor is biased here. And as long as the output voltage across the transistor doesn't drop below a minimum voltage, which is this point, your transistor remains in the active region and it will behave linearly. And therefore, it will produce this constant current irrespective of the the voltage variations. Same goes for voltage reference. When you design voltage reference, you want it to be constant irrespective of variations in the load, variations in the supply, etc. So the purpose here is to demonstrate you. Let's say I am generating a reference voltage V out. This can be one of the voltages to another block. For example, I will use an operational amplifier here, and this voltage reference comes here. Okay. So here is my circuit, for example, right here. Okay. And here comes the reference. So I want this to be a constant. If there is a variations in the temperature, it should still remain constant, right? So now let's see what I'm doing here. I'm using a 5-volt power supply, that is a constant DC voltage source. Then I'm using a resistor to get the current out of it. So that is my current I in, and I am letting that current pass through the transistor. So it has a components like collector current. It is coming here, coming here, coming here. Then it has a base current, and then you have this emitter current. So the first thing, what I want to bring to your notice, I have shorted the collector and the base pins of the IC. So I have 3 pins, and the base and the collectors are shorted together, making this Q1 transistor, which is an NPN transistor, acts as a diode. So it is simply, this circuit is simply as same as you have this V1 5 volts. You have the same resistor R1 flowing through it is then I in, and as if you're connecting a diode. So the current through the diode is your ID, and then that's it. This is your ground. So this circuit is same as this circuit right here. Okay. And now When you force this current flow through the transistor from collector to emitter, you make it conduct, and therefore there is a VBE voltage generated. That is the forward voltage junction drop. And the behavior, the relationship between your current and the voltage, current through the transistor or the voltage, or in this case, current to the diode and the voltage, is that when you conduct the diode here, you also have VBE drop here. Okay. And the relation is your current versus voltage. Let's say diode current and your diode voltage is an exponential behavior. So it's this value is about 0.7 volt to for the silicon diode. So that's it. So let us now calculate the DC operating point by which we will calculate the current value, the voltages generated, and that's the analysis. We call it as an operating point analysis. We have done that a lot of times earlier. And after that, I will explain you this temperature sweep, where I would show you the dependence of the generated voltage VBE with respect to temperature. So we just said that this VBE, V out, is nothing but your VBE, right? And because collector and the base are shorted. So I want it, the VBE, to be constant. However, there is a dependence of VBE with respect to temperature. That is in degrees centigrade. This is in volts. Okay. And this slope is, if I'm right, is minus 2 millivolt per degree centigrade, right? So we'll do that. So let us first understand what the currents and the voltages are into the circuit. So for that, I will for a moment disable this analysis by right clicking here. I will just use this symbol and it is disabled, and this analysis is there. So I will just hit simulate, and now look, I have these voltages and the currents printed on the board. So I have this 5 volt, which is at this node. Let me spotlight it at this node, and then node 001 actually, which is this net, or then V out is 0.81. So here is the for NPN transistor. I haven't selected a special part from the manufacturer, which I can do. I just use the general purpose or generic symbol for the NPN transistor. So V out is 0.81 volt, or approximately 800 millivolts. Then collector current is 4.1 milliampere, and the base current is about 41 microampere, and the emitter current obviously in the opposite direction than the collector current is approximately same as the collector current. So emitter current will be the sum of collector current plus the base current, as we know the KCL. And then you have the current through R1 is nothing but your the sum of, again, the base current and the collector current, which is 4.188. And this the current through R1 is nothing but what is being drawn from this power supply 5 volt same. Okay, so we know that this transistor is biased in the forward as a forward biased diode. It is biased as a PN junction diode. And now you see now on the left bottom, extreme left bottom of your screen, I am also seeing the dissipation in the transistor, which is showing me to be the multiplication of current and voltage. So it comes out to be 3.397 milliwatt. Okay, so that's the dissipation. If I take this DC operating point right here in the bottom left, extreme bottom left of the screen, I get the value of the current also, that is 4.14 milliampere. If I come here, I get the dissipation, and base current is also now showing 41 microampere, and so on. I have this DC operating point of emitter current also. Okay, now with that said, now let us see if we can have this kind of curve. So what I'll do now, I will enable this analysis and I will see that it is okay. And what I want, ideally, the V out should be constant. However, in nature, there is a dependence of VBE, forward voltage drop of a diode. Now the transistor acting as a diode with respect to temperature. So let us simulate it, run, and I would go to schematic where the probe asks me to click to plot V out. I will click it here and now look at this. I see that my voltage is falling from about 800 millivolt at room temperature of 25 degrees centigrade. It is dropping at a linear rate, and up to 100 degree I am having this change in voltage about 700 millivolt. It goes 710. Okay, so this is how I can simulate. I can the behavior of the devices components with respect to temperature. So this is the first time we have brought this analysis in our SPICE tutorials and the circuit design. So remember this, the syntax for that is very simple. Just go to OP and write this command here. So what I have done here, I will right click here. I will show you how I have done that. So I'm using the dot step command to overlay simulation results, right? And then name of the parameter is the global temperature. Name of the sweep is a list. I'm putting the list. First value is 25, then 50, then 75. As soon as you input these parameters, this syntax comes here, what you see here. Okay. What if I choose linear and then start value, then stop value, and the increment I have to it. So let's say stop value is 100, or maybe, yeah, 100. And then you have like increment about, let's say, 5. So it will start from 25, it will stop at 100, and the steps will be 5. So from 25, 30, 35, 40, 45, and up to 100 it will go. And look at this, it will go. And then click simulation, and this is how you now move again the same curve. You are getting that, and look at the change here. I'm getting this. What if I right click again here, and uh, with the linear, octave, decade, whatever you can choose. Let's say I go from the initial one like -40 to 120 at the steps of 5. So I click OK, and I then click it, and you now see I have changed from about 870 millivolt to down to 680 millivolt. So at -40, I'm at 890 millivolt. That's my uh, forward voltage jump. So at the negative temperature, I am getting the increment in the forward voltage drop, and at the positive temperature, I am getting the drop in the junction voltage. So this is how we have simulated this temperature behavior of your circuit, and hope this is useful when you perform any kind of circuit design and you want to understand its performance with respect to temperature. So this is quite handy. You can also do a sweep with respect to your supply. So if you change the supply, you sweep it, your reference voltage which is generated here is likely to change. And as a designer, our goal is to make this reference voltage or reference current in, for example, in another circuit, you will design a reference current. For example, in the current mirror in our previous model, we've seen that. So either current reference or voltage reference, whatever quantity you design, your goal as a designer is to make them independent of supply variations and the temperature variations and the variations in the load that they drive to or they get current from. So that's all. And maybe in future videos, you can see some sweeps from the DC voltage source. This is quite simple. We've covered this in a lot of our earlier videos. So that's an exercise for you. Just sweep this DC voltage source and see how you get the variations in the Vout. So stay tuned for more informative contents like this. And if you like the button, click the like button. If you like this video, then put some comments, share it with others for a wider reach, and stay tuned for more informative contents like this. Till then, wish you happy learning.